In economic dispatch, we assume there's no network representation. If we want to include network constraints in our optimization problems, we can use optimal power flow. We can limit power flows and impose security constraints as preventive dispatch. Optimal power flow problems are high-dimensional, and many control variables are discrete, so they are mixed integral problems. And if we use AC power flow, problems will be nonlinear and non-convex. We usually combine our constraints into Lagrangian functions and use iterative methods to solve. For example, gradient methods and Newton's method. Newton's method is faster because second derivative information is used. But still, it is difficult to handle inequalities according to KKT conditions. So we can use interior point methods or linearized nonlinear problems to use the simplex method in linear programming. Most importantly, the concept of relaxation is practical for large-scale systems. The essence is to start from initial relaxation by ignoring some constraints or setting some discrete values as continuous, and then add violated constraints one by one. In this video, we focus on direct current security constraints optimal power flow and use shift factors to represent generation and network topology changes. The procedure for solving an optimal power flow problem is to solve an economic dispatch problem first and then add network constraints and security constraints. At first, we only have generation constraints and power balance constraints. How exactly are violating line flow limits added? We write the new line flow in the violated line as the original line flow plus generation shift factors multiplied by power change of each generator, which is a linear function of each generator's generation. The next step is to do n-1 security analysis by dropping lines one by one to check line flows. We are not repeating this calculation again and again, but rather using line outage distribution factors. All the added constraints turn out to be linear constraints of generation of each generator. The reason why we use the shift factors we just mentioned is that when there's a generation change or network topology change, we don't want to do the whole line flow calculation again, but rather we hope to use some pre-calculated factors together with the original generation information to represent redispatched power flows. We use three factors. First, generator shift factor. It shows if power at node I changes, how much power flow in line L will change. Therefore, in matrix form, it can be calculated from this formulation. Remember, in DC power flow, there are those relationships between line flows and node power injections, and between node power injections and angles. The line outage distribution factor shows if line K is dropped, then how much that would affect power flow in line L. We inject opposite power flow in lines to represent power outage. If you are interested in the calculation, I can update a video on the details. Basically, it's just assuming opposite power flows on lines and using the sensitivity factors during calculation. The third factor is a compensated generation shift factor, which is used to evaluate marginal power flow contributions of one generator on the other lines when a line is dropped. Finally, if you are doing related research, you'll find the concept of relaxation is practical because more than 95% constraints in such OPF problems are redundant. Thank you for watching, and I'll talk about local marginal price in the next video.